Hello, and welcome to my presentation entitled "A Computable Plant Optimizer Region of Attraction Estimate for Time-Distributed Linear Model Predictive Control." So as many of you probably know, model predictive control is a feedback strategy that computes control inputs by solving an optimal control problem over a receding horizon. So this means that implementation of MPC requires you to be able to solve an optimal control problem faster than the required sampling period of your controller. However, we often want to apply model predictive control to systems that have fast sampling rates and limited computing power. And in this scenario, it's hard to compute the solution to an optimal control problem in real time. So this gives rise to a strategy called suboptimal MPC, which approximates the solution to a model predictive control problem and apply this approximated solution to the closed-loop system. And one particular approach to suboptimal MPC is called time-distributed optimization. And in this approach, we maintain a running solution estimate of the optimal control problem solution and improve this estimate at each time step by performing a limited number of optimizer iterations. And the hope here is that if you do enough of these iterations, that you eventually converge to the optimal solution given enough time. So under a time-distributed model predictive control strategy, the closed-loop system can be represented as the interconnection of two dynamical systems representing both the plant and the optimizer dynamics. So while in optimal MPC, our plant evolves due to a static feedback law that's just parameterized by our current state, in suboptimal MPC, our plant evolves to a dynamic feedback law with an internal state defined as the solution, as our estimate of the optimal control problem solution, which evolves due to a finite amount of optimizer iterations at each time step. So here is a motivating example for our work. Shown on the right is going to be an animation of an inverted pendulum cart system. And what we do is we try to control this system using time-distributed model predictive control. And what we see is that when 5 iterations are used per time step, that the system is actually unstable in the closed loop. But if we do 15 iterations per time step instead, we get asymptotic stability from this initial condition, with a bit of suboptimality due to the fact that we're not computing the optimal solution. The logical question to try to answer is there a way to a priori compute a sufficient amount of iterations to ensure that this closed loop system will be stable? Another question you might want to ask is what initial conditions can we guarantee stability for? And perhaps the last question that you might want to ask is how does initialization of our optimization algorithm at the first time step influence how we're able to obtain stability? And these are all questions that we aim to answer in this work here. So the setting we consider in this work is linear time invariant systems of the form given here. And the reason that we limit ourselves to linear time invariant systems in this study is because we're able to compute many quantities of the closed-loop system in closed form when we assume our system is linear. And the end result of this is we're able to provide computable certifications on the stability of the closed-loop system. So the control objective here is to stabilize the system to the origin, subject to some pointwise state and control constraints for all time. And of course, we aim to use a time-distributed MPC strategy to do this. And shown here is the following parametric optimal control problem that defines our MPC strategy. It's a fairly traditional linear quadratic MPC strategy that you might find in many places, where we enforce our input constraints explicitly in this inclusion here. And while we don't enforce the state constraint explicitly in the optimal control problem, what we will do is we will implicitly satisfy the state constraints by ensuring that we stay within an invariant set that lies within our state constraint set. So having defined this optimal control problem, we make the following 2 assumptions to ensure that the optimal MPC law is stabilizing. And these are just some assumptions on the A and B matrices, the positive definiteness of our weighting matrices, how we choose our terminal costs, and how we define our state and input constraint set. So as previously discussed, the closed-loop dynamics of a system controlled by time-distributed model predictive control can be represented by an expanded state space system. And here, the optimal control problem solution estimate Z sub k evolves according to some optimization algorithm T under a fixed amount of iterations L, and the plant dynamics evolve according to our given LTI system. And the optimization algorithm we choose for this analysis is the projected gradient method, which is given by this recursive definition shown here. And the reason we choose the projected gradient method is because it can handle input constraints very explicitly and also has a very well-defined convergence rate, which helps with the analysis of the optimizer subsystem. So to begin the stability analysis of the plant optimizer dynamics, we're going to define a few quantities. First are S and V, which are the solution mapping and the value function of the optimal control problem. And next are these functions phi and psi, which will eventually show that these constitute components of a Lyapunov function of our closed loop system in the expanded plant optimizer space. So the way we're going to try to prove stability is prove that these functions phi and psi are decreasing in time if we apply our ThA15 control strategy given enough iterations. So with this objective in mind, here's our first major result. And it says that the time evolution of these functions phi and psi can be upper bounded by their previous values with some associated constants that are also dependent on the amount of iterations you perform, which is what this term represents here. And these other constants that you see in the inequality are all constants that we can compute in closed form as a function of the problem data. So what this allows us to do is analyze the right-hand side of these inequalities and show that the right-hand side of these inequalities actually converges to zero under certain circumstances on the amount of iterations you perform. And of course, if the upper bound converges to zero, we must also have that this quantity that we're bounding also converges to zero itself. And this is the logic by which we're going to try to prove stability of our closed loop system. But before we're able to do that, we have to note that these inequalities actually only hold if your state initially starts in some set that represents the optimal MPC region of attraction with the associated optimal control problem. So in order to make sure these inequalities hold for all future time, we identify an invariant subset where these inequalities will always hold. So given if you perform enough iterations, this set sigma is going to be forward invariant under the time distributed model predictive control law, where this set sigma is just a Cartesian product of sublevel sets of these functions phi and psi. So if we assume that our initial plant optimizer state starts in this set sigma, then these inequalities that we mentioned previously will hold for all future time. So to analyze the stability of our closed loop system, we use a method discussed in reference 2, and that is to define this positive linear auxiliary system that represents the upper bound of the inequalities here. And if we can show that this positive linear auxiliary system is asymptotically convergent, then this also must mean that the left-hand side of our inequalities, which are upper bounded by the auxiliary system, are also asymptotically convergent. So by modifying the proofs in references 2 and 3, what we can prove is that given enough iterations of our time-distributed model predictive control strategy, that our linear auxiliary system is asymptotically stable and has a known Lyapunov function. So given this fact, it doesn't take too much more work to then prove that our closed loop system in the variables that we sort of care about, which are the optimal control solution and our plant state, are also asymptotically stable given the same amount of iterations performed. And moreover, we have that the region of attraction of this system is our set sigma that we discussed previously, which is just a Cartesian product of sublevel sets of phi and psi. And we have that this function, which is a linear combination of phi and psi, is a Lyapunov function in this set. So in summary, what we have proven is that if we do enough iterations with our time-distributed model predictive control strategy, then our closed loop system in the expanded state space is asymptotically stable, and with an analytical region of attraction estimate sigma, which we can compute, and with a known Lyapunov function. So now we'll show an illustrative example to demonstrate some of these theoretical concepts. The example we consider is a linearized model of an inverted pendulum. And we use the linearized model for both the simulation itself and the model in the MPC controller. And the continuous time model is shown here. We discretize this continuous model both in simulation and in the model itself. And the simulation parameters can be shown here. What particularly notable is the input constraint set shown here and the state constraint set shown here. And our time horizon is 0.1 seconds with a length of 3, and our MPC weighting matrices are just identity. And given this problem data, we can calculate our iteration bound for stability, and that's 116.2. So if you do 117 iterations or more, you're guaranteed asymptotic stability and a region of attraction estimate. So here's a comparison of various sets in the plant state space. As we discussed before, the region of attraction estimate sigma is actually in an expanded state space, including the solution estimate. But what we look at here is just a projection of that onto the plant state space. And that's what we call gamma n, is this projection. So what we compare these sets to is the terminal constrained optimal MPC ROA. So this is sort of the traditional estimate of a region of attraction you get for an MPC controller, which you generate with a terminal constraint. And then compared to our time distributed model predictive control region of attraction. And these purple and orange sets are essentially inner approximations of this region of attraction. So you'll notice in both cases that we have some conservatism in our region of attraction estimate of the time distributed model predictive control region. And this is mainly due to the fact that we don't enforce a terminal constraint in our MPC strategy, because it's difficult to enforce a terminal constraint when you're only doing a limited amount of iterations, since many optimization algorithms can only guarantee enforcing this constraint when you're done the optimization procedure. And you notice in the state constraint case, our region of attraction estimate looks fairly similar to the input constraint case only. But just the differences here is that we have to shrink our region just to fit inside the state constraint set. And because we have invariance of this region of attraction, we're always guaranteed that we're not going to leave the region of attraction. So of course, we won't leave the state constraint set if we make sure that we inscribe our region of attraction inside of the state constraint set. So here's how these region of attraction estimates compare to actual simulation data using our time distributed model predictive control strategy. The green dots indicate initial conditions that we have stability, while the red dots are unstable initial conditions. So when we use 117 iterations per time step, which is just above the iterations threshold for stability of 116.2, we actually get a region of attraction in simulation that's much larger than our theoretical estimate, which is this dotted line here. And it's actually very similar to the optimal MPC region of attraction, which indicates that we have some conservatism in our analytical representation of this region of attraction estimate of time distributed model predictive control. Another interesting result is actually when we use just 6 iterations, we still have this almost optimal region of attraction, which indicates that our iteration bound is also a little bit conservative. But what's even more interesting is when you use just 1 iteration less, you actually obtain an unstable equilibrium for the simulation data. So there's a very quick transition from an almost optimal region of attraction to no region of attraction at all when you use 1 less iteration. This is sort of similar to the results that we derive in theory, that you can guarantee stability when you do enough iterations, but when you don't do enough iterations, you sort of can't make any guarantees at all.